Hey, this is Mr. A, and I thought I would go over the classwork on elevator type problems because there was a fair number of you who didn't get 100%. So let's talk about these two problems, and they come directly from the practice test. And what I did was I took the question and I broke it down into easier steps. My concern was that if they ask you the question in brief, that you wouldn't know that you had to do all these steps. So that's why I broke it out into steps. First of all, the rocket problem is basically a rocket taken off of the launch pad, and some of you drew me in a nice picture here. A rocket weighs 2.0 times 10 to the 7 newtons. What is the rocket's mass? Okay. First of all, we need to recognize that weight is a force, and it is equal to the mass times the acceleration of gravity, g. Recognize that this is just Newton's second law. A force is equal to mass times acceleration, but it's just a special case of that. So in order to solve this problem, you would need to rearrange the equation for mass. So that would be 2.0 times 10 to the 7th divided by 9.8, and you should have gotten an answer around 2.0 times 10 to the 6th. Kilograms, right? The rocket engines generate 2.5 times 10 to the 7 newtons of thrust at liftoff. Draw a free body diagram illustrating the weight force Fg and the engine force. Okay, so we always represent the object as a dot, and the object is going to have the force of gravity pulling on it down to the earth, but hopefully our rocket engines can generate a bit more thrust. Now take care to make sure that your free body diagram does communicate the fact that your F applied is greater than your Fg. Right? So draw a free body diagram illustrating the weight force Fg and the engine force applied. Okay, so that's what this looks like. Add the force vectors to determine the magnitude and direction of the net force. Okay, show your work and show F net vector in your free body diagram at right. Well, if your F applied is greater than Fg, then you're going to get some F net force that's going up. We want our rocket to go up, right? Over here we need to show our work mathematically, so F net is equal to F applied plus a negative Fg. Negative Fg because this vector is pointing down. We are told what F applied is. 2.5 times 10 to the 7. And we are told the rocket's weight. Plus a negative, or just let me write negative here, minus the rocket's weight, 2.0 times 10 to the 7. All right? That's going to leave us with a net of 0.5 times 10 to the 7, or 5 times 10 to the 6th newtons. Okay, so that's what the value of F net here is. Given the net force and mass of the rocket, calculated above, use Newton's second law to determine the acceleration of the rocket at liftoff. So, Newton's second law, this force is the net force, this mass is the mass of the rocket, and the acceleration is what we're going to calculate. It's our unknown. There's some confusions here about the acceleration of the rocket at liftoff and the acceleration of gravity. I saw some students' papers, and they had FG is equal to 9.81. No, the acceleration of gravity is equal to 9.81. FG is equal to mg, right? FG is equal to mg. F net is equal to the F applied minus FG. I know there's a lot to keep up with here, but you need to understand that this acceleration is acceleration of the rocket launching into outer space. So this is what we're going to solve for, so we just need to rearrange this equation. A is equal to F net divided by the mass of the rocket. F net we calculated up here, 5 times 10 to the 6th newtons, divided by the mass of the rocket, which we calculated up there, 2 times 10 to the 6th. Okay, and this is kilograms. Okay, so this is just 5/2. Now I'm going to expand. I'm just going to make sure our units work out here. This is meters, kilograms, seconds squared, divided by kilograms, and so our kilograms go away, leaving us with 2.5 meters per second squared, and that is an acceleration. Okay. Our second problem is a more traditional elevator type problem, and we are given the mass of the elevator and that it accelerates upward at 0.45 meters per second squared. So drawing a free body diagram, there is some force applied on the cables, and there is some force of gravity, and then there is some net force which is causing it to accelerate upward. Okay. Use Newton's second law in the given information to determine the net force. So net force, and we have a couple of equations for the net force. We have F net is equal to mass times the acceleration of the elevator as it goes up, and we have F net is equal to the applied force minus the force of gravity. Okay, so we are told what the mass is, and we are told what the acceleration is, so we can find F net easily enough. So we needed this first equation, didn't we? So F net is equal to the mass, 1.10 times 10 to the 3 kilograms, times the acceleration, which is 0.45 meters per second squared. Okay, and that is going to equal 495 newtons. So now we actually have a value for F net, 495. Use the net force is equal to the sum of all forces to determine the magnitude of the force acting on the elevator cables. So that would be our F applied. We know, let's see, F, so that's where we use our second equation. F net is equal to F applied plus the negative FG. Have we figured out what our FG is? No. I'm going to write that I'm going to write FG up here just because I didn't give you a lot of space. Fg is equal to the mass of the elevator times the acceleration of gravity, which is 1.10 times 10 to the 3 kilograms times 9.81 meters per second squared. And so the mass of the elevator is approximately 1.1 times 10 to the 4. Since that number is like 10, it's just like really multiplying 10 times that. So we're just really, in scientific notation, we're increasing the exponent from 3 to a 4. So now we know what Fg is, we know what Fnet is, we just need to rearrange this equation for F applied. F applied is equal to Fnet plus Fg. Fnet is equal to 495 newtons, and Fg is equal to 1.1 times 10 to the 4 newtons. And this is going to be approximately equal to 1.15 times 10 to the 4 newtons. That's what I did it, but some of you, if you carried all your numbers, this is with sig figs, you probably got a number like 11,286 newtons without sig figs. So I was looking for either of these two. Okay.